Hi, in this final video on forces, what we're going to do, we're going to look at energy and power and how that relates with forces. The learning outcome is, as you can see here, use the principle of conservation of energy and appropriate relationships to solve problems involving work done, potential energy, kinetic energy and power, which is the very last one there. So what does this mean? Well, again, this is a bit of a revision from National 5. We looked at force, energy and power, so we'll just do a very, very quick recap and then get a worked example. So forces, energy and power. Power Here we go. Power is defined as the rate at which energy is transferred. Power is measured in watts. Power P So power is measured in watts. Energy is measured in joules. Force obviously is measured in newtons. So power and energy relate to each other as E is equal to power times time. So the watt is joules per second. But this is your formula for energy, power and time. Then for energy, what we have is we're going to have three different types of energy. So energy we're going to have work done, is going to be energy W is going to be force times distance. We're going to have kinetic energy, so EK half mv squared, and we're going to have potential energy. More fully, this really should be called gravitational potential energy, but it's almost exclusively referred to as potential energy. P is equal to mgh. Okay. So if we look at this in a kind of practical example, I guess that let's have an object, and if you're going to push an object up a hill, object will have a mass of m. The hill will have a slope of theta. Have a length of d. Now, so pushing this object up the hill require us something to apply a force to it. So pushing the object up the hill requires work. The amount of work that will require will be force times distance. Now in this case, if we're going to push it at a constant speed, then the amount of work that we will have to do and the amount of force that we have to apply to it will have to be equal and opposite to the downslope component of force. That's the only thing. So force required is going to be force downslope, G is equal to mg sine theta. As the object moves up towards the top of the hill, the force that we're applying, the work that we're doing, is going to be getting converted into gravitational potential energy. So we're going to have now a height at the top of the hill So at the top of the hill, object has gained EP, which is mgh. So now this energy from the object at the top of the hill will be stored, and at some point then the object can be released back down. So if object is released, then EP will be converted into EK, which is a half mv squared. So let's look at an example. As I say, I don't want to spend too long on this because this is something that we've done in National 5, and so already. So let's just say, for example, we'll have 30-degree slope. It's got a height of 80 meters. Emily is on a skateboard here, and she's been pulled up the ramp by this rope that's attached to the motor. It's going to be getting wound in, and so she's going to be getting pulled up. We're going to assume that she's traveling at constant speed. So we'll ask, first of all, what force is required to pull Emily up the slope. So Emily has a mass of 60 kilograms, and we're just going to have F equals mg sine theta. So F equals mg sine theta. Sine 30. It'll just be 294 newtons. Then we can have calculate the work done. Pulling her to top of slope. Now we're going to have EW is equal to force times distance. Now we need to figure out the distance. So the distance is going to be this distance here, and if we've got an angle and we've got a height, then we can work out distance just with some trigonometry. So you'll have their opposite. So sine theta is opposite over hypotenuse. To get our hypotenuse, which is going to be d, we're going to have 80 over sine 30. Sine 30 is a half, and so the distance of the slope is 160 meters. Pulling with a constant force, 294 times 160, and that will be 47 kilojoules of energy. Okay. If it takes 30 seconds to pull Emily up the slope, calculate the power of the motor. Now, in this case, we're going to assume no energy losses. I can do what I like, so let's just assume, make it easy, that no energy is lost, and we will have power is equal to energy over time. Now 47 kilojoules, 47 times 10 to the 3 over 30 seconds. And that's going to be 1,570 watts, so 1.6 kilowatts. Okay. Finally, we can have Emily lets go of the tow rope when she reaches the top. Calculate her velocity when she reaches the bottom. Again, we're going to ignore any effects of friction. Now, the motor is providing energy. That energy is doing work on Emily. Emily is getting pulled up the slope. The amount of energy that the motor uses will be transferred to Emily in the form of gravitational potential energy. As she releases the tow rope at the top, she rolls back down. That gravitational potential energy will then be reconverted back into, or converted into kinetic energy. So we'll have a bit of a list of so EW, so the work done by the motor, is going to equal the EP at the top, which is then going to equal EK at the bottom. Now we know what the work done was 47 kilojoules, and so we can just have EK is equal to half mv squared which will give us V is equal to the square root of 2ek over m, which is going to be 2 times 47 kilojoules and that will give us a velocity of, let's say that's 40 meters per second. Okay. 40 meters per second is an incredibly high speed, and it's never really going to happen in the real world. We're going to have things like friction, we're going to have air resistance. Air resistance is obviously going to be the biggest effect of that, and so she would nowhere near get to that speed as she's rolling back down the hill. She would in fact reach her terminal velocity much sooner than that, probably somewhere around about 13 meters per second. But as an example, that's the kind of thing that we can do with energy, power, and work done. Okay, thanks for watching. Bye.